Lesson 423, independent and dependent conditional probability. Okay, so we're going to jump into the first example. It's kind of like a discovery lecture as we go. So say you randomly choose an item from the box above. As we studied, the past units of probability of choosing an item would be the probability of getting that item is equal to that item over possible outcomes. Okay, and that we've had a ton of practice with. Okay, so just a quick thing, the box, I actually moved it down here to the bottom. It just so happened that way. So let's look at our scenario. It says picking two items and replacing them after each pick. If we replace an item before we pick the next, the picking of the items are independent. So imagine we have all these hamsters, robots, cheeseburgers, candy, and scorpions. Imagine all these guys are in a bag, right? There's a total of 16 of them. So we go in for our first pick. Let's say we pick a cheeseburger. We're a little hungry. We smelled it a little. Remember, you're not looking at it. This is random. So you go in, you pick it out, and you pick out a cheeseburger, right? Hopefully you're not picking out a scorpion. So you pick out this cheeseburger, and you look at it, and you say, oh, it's not that good. And you put it back into the bag. Now the chances, now we got to look at see what the chances of it are the second time. Okay, so first draw, the probability of getting a cheeseburger, it's also right there, but we have 3 out of 16. 3 out of 16. Now we put it back in the bag, so now we have back at full sample space. You put it back in the bag, you stick your hand in again. Let's say this time you pick out another cheeseburger. The odds of getting that again are 3 out of 16. Those are both equal. Okay? Since they're both equal, the odds don't change. None of your odds change. You still have a 3 out of 16 chance for picking a cheeseburger because you put it back into the bag. So when it's asking why it's independent, it's because the probability P-I-C-K of picking a certain item remains the same after replacing. Okay. Now let's look at some examples. Okay, so independent, remember that we use probability of A and B happening is equal to the probability of A times the probability of B by itself. Okay, so probability of A and B. So pick 1 is a scorpion and pick 2 is a scorpion. So probability of picking a scorpion for 1, so we got 6 here, right? That's 6 out of 16. Or you could look on the previous page and you can get it off there. So that's 6 out of 16 times the probability pick 2 is a cheeseburger. So we're looking at cheeseburgers this time. That's 3 out of 16, right? And that's equal to the probability of A and B. So now we multiply those out. That's 6 times 3 is 18. So these multiply out to 18. 16 times 16 is 256. So for probability, I'm looking at 18 over 256. That's about a 0.0703 chance that pick 1 is a scorpion and pick 2 is a cheeseburger. Okay. Now next one, we're looking at pick 1 is a hamster. So I'm going to go straight to hamsters. It looks like I have 4 hamsters out of 16 times. Pick 2 is a hamster. Remember, we're putting the hamster back, so we still have, on our second pick, we still have 4 out of 16 hamsters. And that's equal to the probability of A and B. So the probability of A and B happening is going to be the same exact thing. So if we simplify this, 4 times 4 is 16. And 16 times 15 is 256. We got that from earlier. So 16 divided by 256 gives us a 0.0625 probability that pick 1 and 2 are hamsters. Okay. Pick 1 is something that you can eat. So realistically, you can't eat a hamster, you can't eat a robot, you can't eat a scorpion. So the stuff that we can eat are in the middle. So that's cheeseburger, 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 candy. That's 4. So 4 out of 16 times pick 2 is an animal. So we got all of our little hamster buddies here. 1, 2, 3, 4 hamsters, and we have 6 scorpions. So that's 10 out of 16. And that equals 40 out of 256. 40 divided by 256 gives us 0.15625 probability. Okay. Now we're looking at pick 1 is candy. So candy is 1 out of 16. We only got one piece of candy in there. Times pick 2 is a robot. Robots are 2 out of 16. And again, that's going to equal to the probability of candy and robot. Okay, and since they're independent, it doesn't, the fraction, they can put vice versa. So 1 out of 16 times 2 out of 16 gives me 2 out of 16, and 2 out of 16, 2 out of 256. Out of 256, that is a 0.0078 probability. Okay, next, pick 1 is a candy. That's 1 out of 16. Pick 2 is not a candy. So not a candy means everything other than candy. So not candy, which is the 15 other stuff in there. Okay. So 15 times 1 is 15. 16 times 256. So now 15 divided by 256 gives me 0.0586. Okay, next one. Looks like we got 3 picks here. So pick 1 is a candy. So that's, I'm going to erase that. Pick 1 is candy. That's 1 out of 16. Times pick 2 is a robot. That's 2 out of 16. And pick 3 is a hamster. 4 out of 16. Okay. Multiply these out. 2 times 1 is 2 times 2 is 4. 16 times 16 times 16 is 4,096. And 4 divided by 4,096 gives us a very small number, 0.00098 probability. Okay, so again, this was for independent, so it doesn't matter what the first one was. Well, the second one doesn't depend on the first one. Okay, now going on to dependent events. So the conditional probability of dependent events. So in the first example, we put it back in the bag. In this example, we're going to pick out our cheeseburger and we're hungry, so we're going to eat it. So that means that there's one cheeseburger that's gone out of the bag. Okay. So since we are not replacing the first item before picking the second, the picking of the 2 items are dependent. So let's see why. Okay, and let's go back to the cheeseburger. So on the first pick, if I pick out my cheeseburger, right, and that's what I wanted. I wanted a cheeseburger. I was hungry. Candy's not going to satisfy it, my hunger. So for the first pick, we have a 3 out of 16 chance that we get a cheeseburger. Okay, and now on the second pick, keep in mind that we ate this. This is not in the bag anymore. We did not replace it. Right? So now if we look at our sample space, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this one is going to be out of 15. Notice how that changed. It's because we didn't put back the cheeseburger. We ate it. So now in that bag, I'm going to erase that too. What are the chances of picking a cheeseburger again? So it's 2 out of 15. I mean, anything else in there, right? Because this is going to be gone. Let's say we wanted to pick a robot, or let's say we wanted to pick out a hamster. So the chances of picking a hamster are 1, 2, 3, 4 out of 15. The chances of picking a scorpion are 6 out of 15. Hamburger, 2 out of 15. Robots, 2 out of 15. So let's say we wanted to pick out a hamster. That'll be 4 out of 15, right? So cheeseburger, hamster. Okay. So now we gotta explain why they are dependent. It's because the first straw affects the outcomes of the second draw. Okay? So keep this in mind too. Imagine if you wanted a piece of candy. If you wanted a piece of candy, someone before you, right, you're going to draw second. Someone draws first and they get the candy, right? They had a 1 out of 16 chance to get the candy. They got the candy. Now it's your turn. All you wanted was that candy, but now that candy's gone. So you have a 0% chance of getting that candy. Okay, so it's dependent. If you lose the opportunity to get that candy, it's a dependent event. Okay, and this kind of shows us the equation that's going to come with it. So to find out what to do, we start with the conditional probability model. So this is the probability of A given B. Okay, and we did this before, so they're just going to be doing some algebra here. So it's the probability of A and B divided by the probability of B. Okay, so they're multiplying each side. Okay, and I'll do this in blue. So they went ahead and multiplied each side by the probability of B, right? It's the probability of B. Probability of B. So that's what's in red over there. And that is so they can cancel out these probabilities of B, right? And this is what you're left with here. So you have the probability B times the probability of A given B equals probability of A and B. Okay, so here's what it means. So back to the cheeseburger. So we picked one cheeseburger. Okay, so whoever picked first picked the cheeseburger, right? That was a that was a 3 out of 16 chance. Now, 2, the second person that picks, this is going to be our second person, right? Because this is telling us that B has already happened, right? And B was the probability of getting a cheeseburger. It's already happened. So now it's asking, what are the chances of getting a scorpion, right? Getting a scorpion given that someone took a cheeseburger. So we go up here, we cross out our cheeseburger. Well, what are the chances of getting a scorpion now? The chances are 1, 2, 3, 4, 5, 6 out of 15, right? Because we didn't put that cheeseburger back in. And that's going to equal the probability of getting a scorpion and a cheeseburger, which would end up being, 18 over 16 times 15, 240, which equals 0.075 or 77.5%. Okay, so now let's do these examples. And we're going to be using the same chart, the same hamster, robot, cheeseburger, candy, scorpion chart. Okay, so this time we're not replacing. Okay, we are not replacing them. So once you pick it out, it's gone. It's not going in the bag. The bag is moving on. Okay, so pick one is a scorpion. So if pick one is a scorpion, we're looking at our scorpions. They're 6 out of 15. Okay. Times pick two is a cheeseburger. So imagine one of our scorpions are gone. Pick two is a cheeseburger. Now we're looking at 3 out of 15. Oh, ooh. That should be 16. Got ahead of myself. Okay. So scorpion is 6 out of 16. And now picking a cheeseburger is 3 out of 15, which is equal to, and this is the same odds we had earlier. This was 18, and this I believe was 240. So we're looking at 18 divided by 240 was 0.075, 0.075 probability here. Okay, now let's see if pick one is a hamster. Let me erase my scorpion that I crossed out. So if pick one is a hamster, goodbye one hamster. So hamsters were 4 out of 16 times. Now pick two is a hamster. So now we're looking at, so for the second pick, we only have 3 available hamsters. One is gone. So that's 3 out of, the sample space is 15, which equals 12 over 240. And 12 divided by 240 gives us 0.05. Okay. So pick one is something you can eat realistically. Something we can eat realistically, and that was going to be these 4 here, right? The 3 cheeseburgers and the candy. So that is 4 out of 16. And imagine that we picked, let's say pick the candy, the edible one. Times, pick 2 as an animal. Animals are now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 out of, now the sample space is 15 because one of the edibles are gone. Okay, so this gives us 40 out of 240, which is 0.1666, and that's going to be forever. Okay, and remember you can change these to percents, move it twice, 16.66%. All right. Next one, pick one is a candy. So candy is 1 out of 16 chance. So we pick the candy, we're not putting it back in, we're eating it, times the robot. Pick 2 is a robot. Looks like we have 2 robots left out of 15 total, which is 2 out of 240. And 2 divided by 240 gives us 0.0083. Okay. Next one, pick one is a candy. So candy again for pick one. So 1 out of 16 chance times pick 2 is not a candy. So not a candy. So imagine if we pick this out. So now pick 2, which is not a candy. So remember, we have a total of 15. And if you look, the stuff that's not a candy is all of it, right? All 15 of those items is not candy. So that's 15 out of 15 that is not a candy. Right, that's 100% of the stuff. So now we do multiply across. That's 15 over 240. And 15 divided by 240 gives us 0.0625. And our last one there, I'm going to do this one in red so it doesn't get mixed up with the other one. So pick one is a candy. So we got candy again. So candy is 1 out of 16. And that's gone. Pick 2 is a robot. So we have 2 robots out of 15. All right, so we picked a robot. So we got to cross a robot out. And now for the third pick 3 is a hamster. So hamsters, looks like we have 4 total hamsters out of This time we didn't put 2 of the items back in, so we're down to 14. Right? The sample space is now 14. So now working this out, let's see, 1 times 2 is 2, times 4 is 8. That's 8 out of 16 times 15 times 14 gives us a 3,360. So 8 divided by 3,360 is 0.0023, let's just say 4. Okay, so that's a very small percentage. If you look at that, that's a 0.24% chance, very small percentage. Okay. Now it says compare your probabilities that you have calculated above to the probabilities in part 1. Is there a noticeable difference between the probabilities of an independent and dependent event? Okay, so let's look at these. Let's look at the first one. We got, for the top left, we got 0.75. Here we got 0.0703. It looks like 2 is higher, right? So I'm going to put a star by 2. Let's look at this one here, the second one. We got 0.05 or 5%. Let's see what we got on the other one. 0.06. So this one's higher. Let's look at the next one. So we got 0.116 here on the blue. 0.116. So this is higher. This one was higher. Okay, let's look at the green. 0.0083. 0.0078. This is again higher. Pick one as a candy, or let's do the one in black here. 0.0625. 0.0586. Dependency is higher. And the last one, 0.0024 and 0.00098. This one's higher. So the thing that we notice is that you have higher probabilities I'm pretty sure I spelled that wrong. Higher probabilities when we have dependency. Okay, and real quick, we can do these ones. They're practice problems that relate directly to what we just did. So let's try the extra example 1. Your teacher passes around a box with 10 red pencils, 8 pink pencils, and 13 green pencils. If you and the 2 other people in your group are the first to randomly select a pencil, what is the probability that all 3 of you select a pink pencil? Okay, so let's look at the pinks. Let's first figure out how many total pencils we have. We have 10, 8, and 13. So it looks like we have, 31 pencils here, right? You do 10 plus 8, you just combine all those. So we have 31 pencils. 31 pencils. Now, let's say that I go first and I pick a pencil. The chances of me getting a pink pencil, right? All 3 of us are going to get pink pencils, is 8 out of 31, right? And we're not putting these pencils back in. Once you pick your pencil, you're stuck with it forever. So now we have 8 out of 31 pink pencils. Times, now the box gets shifted over to my partner that's in my group. Now what are his chances of getting a pink pencil? So I already have 1 in my hand. So now this goes down by 1. Right, so now he has 7 available pink pencils out of, instead of 30, remember that I picked 1 out, I'm holding 1 out of 30. Times Okay, so now it gets to the third person in the group. So I got a pink pencil. My partner has a pink pencil. So 2 pink pencils are gone. How many are left for the third person? So 7. 1 just got picked. So now we have 6 available out of, remember we started with 31. I picked one, that's 30. My partner picked one. So now that's 29 pencils left. Okay, so now the probability that all 3 of us get a pink pencil is going to be 8 times 7 times 6, which is 336, over 31 times 30 times 29, which is a huge number, 26,970. And if we're looking at that probability, 336 divided by 26,970 gives us a 0.0125. Okay, and again, if you're looking at percentage, that's only a 1.25% chance that we get pink, pink, pink. So now let's look at that follow-up question right below it. What is the probability that your group members do not randomly select a green pencil? So again, remember we're 3 people and we're not selecting green-red pencils. Oh, sorry, green pencils, colored pencils. Okay, so now let's figure out how many are not green. So if they're not green, they're either pink. They're either pink or they're red. And total, we have 18 of them. So they have out of 18, well, 18 out of 31 probability to select a pencil that is not green. So if the first person selected a colored pencil and is not green, that means that there's 17 not greens left, and there's 30 left in the box. And now for the third person, right, we want to do the same thing. So now for them, if they choose out of the bag, there's only 16 that are not green that are left in there, right? We get 1 less each time. We're looking for not green. And this is out of this time a sample space of 29. Okay, now we multiply these out. 18 times 17 times 16 gives us 4,896 over 26,970. 26,970. Oh man. Okay, so now put it in our calculator. 4,896 divided by 2,6,970. That is a 0.1815. Or if you're looking at percentages, 18.15% chance that we're not going to be selecting, that all 3 of us don't select a green pencil. And let's go on to the last example here. So it says Harper keeps her textbooks in her locker. She has 1 math book, 2 French books, and 2 history books, 1 biology book, and 3 English books. Harper grabs 2 textbooks at random. What is the probability that both books are history books? Remember, we're not putting these back in. So what is the probability that the books are history books? So first let's figure out how many books she has in total. She has 1, 3, 5, 6, 9, 11. So it looks like she has 11 books. Okay, so I'm just going to write that off to the side. Total 11 books. And I'm going to double check that. So we got 3, we got 2, 5, 6, 8, 10, 11. Yep, 11 books. So what is the probability that both books are history books? So let's say she picks her first one out. The probability that she has it be history, looks like she has 2 history books, is 1 out of 11. Now times remember that she picked one of these history books out. Now the second time, what are the chances of her getting a history book again? She had two. She picked one. She only has one left now. And there's only 10 books left in her locker, right? Because she had 11. She picked one out. She's holding her history book. So there's only 10 books left in her locker. So now her probability is 1 out of 110. 1 divided by 110 gives us a probability of 0.0091. Or if you change it to a percent, 0.91%. So it's pretty unlikely that if she just chooses these books at random, that she's going to get history back to back. What is the probability that both books are English books? So let's look at her English books. She has 3 English books. So the first book she picks is an English book. So if she picks the English book, I actually just noticed that I made a mistake on this first one here. Oops. This should be 2. Got a little ahead of myself. Okay, so just going back to that one, what's the probability that both books are history books? So the first one, she has a 2 out of 11 chance. And then she has one book left after she picks one for her first pick. So that's going to change all this. So that's 2 out of 110. And 2 out of 110 gives us 0.01818, or a 1.818% chance. Okay, going back to the English books. So the English books, she had 3. So that's 3 out of 11 that are English. So first pick, she picked out an English book. Now second pick, remember she already picked one. So there's only 2 English books left. So that's 2 out of 10, right? Because there's only 10 books left. There's 2 English books left in the locker and total of 10 books. So this is 6 out of 110, which is 0.0545, and percentage-wise, 5.45%. So a little higher chance that both books will be English. What is the probability that one book is math and the other book is a biology book? So one book is math, so she has one math book. So to pick a math book, that's a 1 out of 11 chance, times the biology book is also 1. So now biology, we have 1 left in there, right? Because she didn't pick the same book over and over again. So probably that one book is a math book. That's 1 out of 11, right? And now her second pick, she's picking again, but this time she's looking for a biology book. The chances of getting a biology book are still 1, right? Because there's 1 biology book in there. But this time it's out of 10, right? So this time the numerator doesn't change because it's a different book. So now we get a 1 out of 110 chance. So let's do 1 divided by 110, and that's 0.0091. So 0.91% chance. So fairly low, less than 1%. Okay, and that last question there, what would Harper have to do to make the book choosing independent? So remember, independent, the odds have to remain the same. So you have to have the same chance of picking a book out the first time and the second time. So to make it independent, she would have to replace the book. So she would have to put it back amongst the sample space.